Welcome back. John Valvano still here. I'm glad you had a good weekend, I hope. Somebody did, some shaking. All right, so we're going to talk about FixedPoint today. Let's see if I can find my Alt tab. There we go. All right. Last time we introduced this notion of an embedded system, and let's list what were the important concepts from last time. And I would say that real time is probably the most important. So if we were to define real time, what was it? Real-time system is one which behaves in what way? I have a problem, an event, a crisis, a situation, a change, and something that I'm supposed to do something about. Okay? And so what do I need to do to respond to this event? I first have to detect that it happened, right? So I'm going to detect that this event occurs, and then I'm going to respond to it. And what does it mean to be real time? What was the question?
Respond within like a certain threshold.
In order to, that's exactly correct. In order for this to be real time, I have to respond the time between the event and the response. That time has to be less than some upper bound. Okay, and this time is called latency. So this latency, okay, and if I can respond, and we'll see how we're going to do it, we're going to use interrupts, etc. But today, we're going to talk about fixed point numbers. Okay, so we're going to talk about what fixed point numbers are. Again, this is a review of 319K. We'll talk about why it is we use them, when do we use a fixed point, and then more interestingly, how we get it done. As you know, integers are counting numbers, 1, 2, 3, 4. And whenever we want to represent something that's non-integer, we can do it two ways. We can represent it as a fixed point number or a floating point number. And a fixed point, so what is a fixed point number? A fixed point number is the following equation. In other words, the value that represents this non-integer value is a combination of an integer, which we're going to put in a register, we're going to put it in memory, we're going to calculate it on it, times some constant, which is fixed. Okay? Now, if that constant happens to be a power of 10, like it will be in Lab 1, we'll call that a decimal fixed point number. And when that constant is a power of 2, like the bunch of examples we'll do in this lecture, we'll call that a binary fixed point. And if you look at a floating point number, it looks very, very similar. Like, look at the difference between the binary fixed point and a floating point. The equation's almost the same. The difference is, with a floating point number, the exponent is stored, remembered, and calculated, and not fixed. All right. So that's what they are. A fixed point number is an integer which we're going to put in our computer, and a constant which we will remember always. Why we use it is to express non-integer values. Okay? And when can I use a fixed point number? For example, if the voltage goes from 0 to 3.3, or the temperature goes from 10 degrees to 40 degrees, we see that the range of values is known, and this range of values is small. If the range of values go from 10 to the minus 6 to 10 to the plus 18th, you may know that range, but that's a large range, and we will use floating point for that. Okay, so how do we do it? Well, again, we're going to decide what this fixed point is. This will be the design. The design of the fixed point is basically choosing that constant and deciding whether it should be signed or unsigned, and whether it should be 8, 16, or 32 bits. That's the design aspect. All right. And as I said, if that constant is a power of 10, we'll call it a decimal fixed point. And we're going to use decimal fixed point in lab. Look at who's got the machine. Okay. What do the numbers look like when you see a number? What does it look like? Give me one of the numbers from Lab 1.
Which one?
Anyone, pick any number.
1.234.
Okay? So the number 1.234 that you have in lab is a non-integer. Okay? And we're going to store that as the integer 1234, and we're going to remember 10 to the minus 3. Okay? So the constant is going to be 10 to the minus 3. All right? And we're going to use that when we have human interactions because that makes sense to us. When we go to the store and when we buy 1.234 gallons, that makes sense to us. We look at our voltmeter, 1.234 volts or 1.234 degrees centigrade. This makes sense to us. But as we see, we're going to use binary fixed point when we perform calculations. Because it turns out, trick question, how long does it take to do a logical shift left on your computer? Right? What is a logical shift left? For those of you who are not dyslexic. Left is what does what to the operation. If I move something to the left 2 bits, what does it do? Multiply times 4. How many bus cycles does it take to do a logical shift left? 0. They're free. Okay? So this architecture is so powerful that we can do a logical shift left while we're doing something else. Okay? And so whenever we want to run fast on this ARM architecture, it's one of those opcodes we didn't teach you in 319K. We'll see it later today. Sometimes it does take one, but we can often trick it. So all right. Here's some terms associated with the design. Obviously, we know whether it's signed or unsigned. That's obvious. In C, how do I tell? Right? If I use a signed type, that's signed. If I use an unsigned type, it's unsigned. The precision is the number of distinguishable values. In this case, it's going to be, in this particular case here, it's going to be 32 bits. And then the resolution is the smallest change in value that I can represent. So we saw that the Lab 1 could represent or could output or could store the value 1.234, and the next larger value is 1.2345. And we see that the delta, which is the fixed point, is also the resolution. And the delta often has units associated with it. Questions? Let's do a couple of examples. All right. All right, let's say we're going to make a voltmeter. If this is your TM4C123 and I want to make a voltmeter, what port am I going to use? 319K. If you had to make a voltmeter out of your 319K stuff, how would you do it?
With the ADC.
ADC. And if we look at the response, the operation of the ADC, the input goes from 0 to 3.3 volts. That's this input here, and then we have a number n, which goes from 0 to 4095, right? And it's a whole bunch of little dots in there. Is this a continuous function? Like I drew it? No, it's a discrete function. This is an integer, right? 4,096 different possibilities, so I'm a little bit light on my math. And so to make a voltmeter, I'm going to flip the axis. What's the resolution of my A to D converter about? The smallest change in voltage I can measure?
3.3 divided by 4,000.
Yeah, that's not about. That's exactly what it is, 4,096. But what is that about? Kilovolt, megavolt, millivolt. That's about a millivolt. That's what I'm going to use to choose my decimal fixed point protocol. So I'm going to convert 0 to 4,096, 4,095, doesn't go up to 4,000, into the integer part of the fixed point number system. Okay? And I'm going to choose a delta of about a millivolt. So I'm then going to choose an integer that goes from 0 to 3,000. Okay, see that? And so now what I want to do is create a mapping. Okay, and I've chosen a decimal fixed point value. Okay, what's the slope? Again, it's not linear, but it's not continuous, but it's the same sort of linear-ish function. It's an A to D converter. And so I need a mapping from one to the other. So I could, I could do something like I equals 3,000 times, we'll call this n, right? That's what I call times n divided by 4,095. I could do that. Okay. But to make it more realistic, I'm going to want to calibrate it because these constants are the theoretical values. And so rather than using the exact theoretical values, I'm going to find a calibration constant A and another calibration constant B. And then I'm going, because this is a calculation, right? Because it's a calculation, what type of math should I use to represent this binary fixed point? So I'm going to pick a power of 2, which is big enough. I got maybe I should have chosen 16 or 32 or whatever. It's a 12-bit data D converter, so 12 bits is probably enough. And so I'm going to find a constant A and B, which I'll program into my system. I'll calculate n. Okay. And I'll use binary fixed point to represent the number, right? This number that I tried to represent as 0 plus some, this B divided by 4,096. Okay. Which would have been without calibration, something like that. Let's do another one. Okay. Questions on that one? We'll do the same thing. Now I'm doing lab 9. I'm going to make a thermometer. So I have a transducer. The transducer is going to convert temperature into resistance. And then I'm going to use a circuit to convert, and we'll learn all about this later, into a voltage, and then I'll use an A to D converter to convert the voltage into a number. Yeah. So I really got the exact same thing I just did, by the way. If I make it map from 10 degrees to 40 degrees, I could see that this value is going to map, if I do it right, map approximately. And it's no longer actually linear, but I'm assuming it's linear here for today because I'm talking about equations. And so in order to make this thermometer work, right, this is temperature here. I need to define the temperature as an integer times some constant. Okay. What's my temperature resolution? Can you sort of guess what that's going to be? Just like our voltage resolution was? Can you sort of guesstimate what my resolution is going to be? My range is how many degrees? 30 degrees. And my precision is what? How many different temperatures are in there? If I zoomed into this plot, how many different points on this line? 4,095, right? 96. Right, divided by 4,096. And that is about, without needing a calculator, we see that that's about 0.01 degrees C. And this is a thermometer. People don't like binary fixed point. Their eyes like decimal fixed point. So what do I design the fixed point number system as? What delta should I choose? 0.01, yeah. So choose decimal, 0.01 C. Notice the delta has units. The other one had volts. This one has degrees centigrade. So that's going to be my defining moment, my defining part of the decimal fixed point value. So to build the thermometer, what do I need? Not this plot, right? I need the other plot. I'm going to flip it over. put n here, put I there, and again, it's going to map 0 to 4,095. It's going to map into 1,000 to 4,000. Okay. So what does 4,000 mean? 40 degrees, right? And so I'm going to need this mapping here. And again, I could figure out the theoretical thing. I don't care. I'm going to use a calibration and convert I equal A plus B times N divided by 4,096. And that was obviously 4,095 right there. Why did I use a calibration coefficient? Why?
To account for ADC error.
Okay, the ADC is not perfect. Remember, so we used the calibration coefficient for the voltmeter. It's not perfect. What else is not perfect in this system? The A to D is not perfect. The transducer not perfect. One more not perfect. Your circuit is not perfect. Okay, so there are imperfections all along, and so I will build the thermometer. I'll calibrate it, and each one I build, I'll have to separately calibrate. Sidebar: when you get to Lab 9, we're not going to use a linear circuit. We're going to use a table lookup because the curve's not straight, but nevertheless. Yep, that's right. Okay. All right, so let's talk about what bad things can happen, okay, when I do this kind of math. And you can see I've put in some constants just so you can see where's the variable and where's the constant. The A's and B's that we showed in the last couple of slides are constants, whereas the N is the A to D converter, and the I is the integer part of the fixed point number that represents, in this case, temperature. Two bad things can happen. The first is the multiply can go awry. What bad thing can happen with the multiply? Overflow. But we can theoretically look at each multiply and decide whether or not it overflows. And it's fairly easy, and that is if I take any two numbers, x times y, okay, and if x is n bits and y is m bits, x times y is how many bits? Right? So if I just take an integer math, when I multiply two integers together, what do I get? How many bits do I get? N plus m. Okay, so I can use that theory to look at this equation. All right. So how many bits is 3,000? 3,000 as an integer is how many bits wide? I know when you implement it, it's 32 bits. When you actually put it into the register, it's going to be in a 32-bit register. But as a theoretical value, what's the smallest number of bits that I could put 3,000 into? 12. 12 bits. Okay. I know it's 4,095 is bigger, but 3,000 bigger than 2,048, so it's 12 bits. How many bits is n? N came from your A to D converter, right? How many bits is n? 12. Okay. So 3,000 times n is how big? 24 bits. Did I overflow? No, it's an ARM. It's got 32 bits. Let's do another one. This one's a little bit trickier. X plus y, where this is n and this is m. Now how many bits do I got? Tricky question. Somebody in the audience is going to have to tell me, well, you have to tell me which one's bigger. I got to tell you which one's bigger. Just for our argument's sake, one of them is bigger than the other, right? Okay? So I'm going to assume here that n is bigger than m, just for argument's sake. Or equal to. They could be equal. So,
Equal, it's n plus 1.
well, if they're equal, it's n plus 1. But if they're not equal, it's still n plus 1. Okay? I'm going to get one more bit than the bigger one. That's theoretically what happens. So now I can look at, well, I should have done the divide. Okay. If 3,000 times n is 24 bits, what is 3,000 times n divided by 4,096? 12 bits. Okay. Zoom, I just lost some bits. That's actually called dropout. We'll talk about that in a second. And so if this portion here is 12 bits, and how many bits is 1,000? How many? The number 1,000 is how many bits? 10. Okay, so if I take a 10-bit number and a 12-bit number and I add it together, what do I get? 13 bits. Okay. Is it going to fit? Yeah. And will it ever overflow? No. Okay. We do have a problem with the right shift and the divide, and that is you lose bits. Okay. We have a problem with add, multiply, and left shift is it could overflow. So add, subtract, multiply, and right shift could cause overflow. In our case, it didn't. But the divide and the right shift cause an error called dropout. And that is I've lost bits. Now, I didn't lose bits here because I first gained those 12 bits, and then I lost them. You see, this operation here made it 12 bits bigger, and then this operation took away my 12 bits and put it back to 12 bits. Whereas this operation here, what is n divided by 4,096? Yeah, 0. So how many bits do I got left? None. I got no bits left. See, this is a really catastrophically stupid thing to do. Okay? And those are the two errors that we want to keep track of. Overflow when I multiply, add, subtract, and left shift, and dropout, I might lose my data when I divide or right shift. So you notice what I'm going to do is multiply first, and then I'm going to shift right or divide. Here's where I'm going to show you where the magic happened. Okay. So again, these are the same sort of equations here and there, and you go, hey John, which is better? Should I divide by 4,096 or should I shift it right by 12? I mean, theoretically, they're what? Theoretically, they're equal, right? Divide by 4,096 is exactly a shift right by 12. But from a let's get it done really fast, good, smart person, which one is faster? Okay, trick question. That's C code. Okay? The computer don't execute no C code. What does the computer execute? Machine code. What does the compiler do? Convert one into the other. And the compiler's smart. You know, how much you didn't pay a lot for this compiler, but you get that little warning that pops up. You know, 32. There's a $10,000 compiler. Okay, so this is boom. It's going to give me the same code, same machine code. If these two lines of C produce exactly the same machine code, now are we going to ask which question about which is better? What's left? Readability, human stuff. Right? What makes you feel good? Which is easier to understand? Which is easier to change? And I'm not sure which is easier. Okay, so we could poll the audience. How many love their divide? It's really clear what I'm doing. Yeah. Ooh, that's going to win. How many love their right shift, left shift, whatever that is? Nobody. One guy. So you should use the divide. You and I, right? Because we're twins. I like my right shift as well. We'll use the right shift because we know it's binary fixed point. That's what we're thinking. The rest of you make the other one easier and just buy a good enough compiler so it generates the same code. Okay? All right. Do you have to program in assembly language in this class? No. But we're going to look at assembly language in a couple of places. We're going to look in assembly language for the issue of overflow because it's not in C that the overflow happens, The overflow happens in assembly, so we'll make sure that when it multiplies, it's really doing a 32-bit multiply. When it does an add, we can see it's doing a 32-bit add. But the other fun part, okay, so this instruction is really clear. What's that one do? What does move R1 3000 do? Come on. R1 equals 3000. That's not too hard. This is ARM architecture procedure call standard. So where's the first parameter? In R0. So R0 is the ADC value. Hey, do you like my label? Like my name? Remember I gave you a name last time, a variable parameter name, which was really crappy. Do you like this one better? I do. Multiply. You remember what you got to remember? Which direction does the operations go? Towards the opcode, with the one exception of the store instruction, which goes the other direction. Okay. So obviously that's multiplying the ADC times. If you add half of the divisor, that'll cause a rounding towards 0 if it's unsigned. If it's signed, yeah, it's a lot more complicated to do rounding. But the adding half of the half of the divisor will cause rounding towards 0. So there's the rounding operation. Moves 1,000 in, and this is where it can do. It adds. It first shifts R0 to the right by 12, and then it adds it to R1, stores the result in R0, and again, ARM architecture procedure call standard returns the parameter in R0. So this is where we see that the shift right required no additional opcodes. All right. Here's another application. Again, this is not a design property for 445L. But suffice it to say, with a little bit of fixed point math, you can do some very powerful filtering. What we're going to do here is sample at 480 hertz. What does that mean? If I say the sampling rate's 480 hertz, what does that mean?
Just under twice a second.
Okay. No, it's 480 times a second. If this were 319K, how would you make it sample 480 times a second? Cystic interrupt would occur at what rate? What rate would you have cystic interrupts at? 480 hertz. And what would you do during the cystic interrupt service routine? Sample. Okay. And what we have here, this is the current sample. This is the sample from 1 time ago. And this is the sample from 2 times ago. This is the filter output. This is the filter from 1 time ago, and that's the filter from 2 times ago. And if you look at the filter, okay, how long is it going to take to do this, right? So how many multiplies do I have? Right? 1, 2, 3. How long does it take to do a multiply? Buzz cycle, right? How many adds do I have? 1, 2, 3, 4, right? 4 adds. And how many shifts? 1. Okay? And so in that short amount of time, I can remove all the 60 hertz out of that sample. Boom, it's gone. So this is the gain versus frequency of this equation. But what can you, the 319K, the 445L of this is how did I represent square root of 2? You see it right there? That's the square root of 2. See it? So in Valvano world, the square root of 2 is approximately equal to what? And don't tell me 1.41423. No, but that's not what I mean.
724.
Yeah, 724 divided by 5. That's my approximation. You see that? And this is called binary fixed point approximation because it's fast and really exciting. Again, not a 445L issue, but the Q of this filter is 6, which is the cutoff frequency, 60 hertz, divided by the 3 dB point, which is going to be 10 hertz. The 10 hertz, this delta F from 1 to the, so it cuts off everything between 55 and 65 hertz. All right. We're going to use it for the display. That's your lab. Again, because it's decimal fixed point. All right. That was decimal fixed point. That was fixed point. What's our alternative? And that's floating point. Floating point, we're basically going to, the value of the number is going to be an integer times 2 to the e. And I'm going to remember both the integer and the exponent. And the base, I don't know of any floating point hardware that use anything other than base 2. Some interesting things about floating point, and I'll just warn you, is when you use some numbers that look like really cool things, okay? Like that looks like a very simple number, right? 0.1. In floating point, you have to approximate it with the same error that we approximate things like square root of 2 and pi. And that's because this has got a factor of 5 in it, and that's base 2, and so we really can't get there. If you look at the single precision floating point, that you have built in your hardware, it actually looks like this format. This is called a mantissa. This one is assumed and not stored. The sign is a separate bit. That means there's actually 2 zeros. There's actually a plus 0 and a minus 0 in this architecture. We're going to have a certain number of bits, binary bits here. And so you could think of this as a binary fixed point fraction, but then we're going to store the exponent as well. So we're going to store both the mantissa, the integer part, as well as the exponent. Like I said, the single precision floating point, that's what's built in your hardware, actually has 23 bits of mantissa, 1 bit for the sign, and 8 bits for the exponent. So right away you can see that in what way is 32-bit fixed point better than 32-bit floating point. Let's say you're trying to represent the numbers from 0.0 volts to 3.3 volts. Which number system is better? And why is fixed point better than floating point for this specific problem? And that is, I got 32 bits here, but only 23 bits there. So the number of just choices in this scheme is a lot less. The exponent's biased. It's a little weird, but that's the way it works. The mantissa, again, has got 23 bits that it's going to store, and this 1 bit that we're going to assume. There's an extra credit in Lab 1, so let me teach you some stuff to do the extra credit. What does the area instruction do? 319K review. What does area data do? It puts this in RAM, right? Because we saw variables have to go in RAM, and area text is going to put this where? Well, where are the 2 places it could go, right? It could go RAM or ROM, and goes in ROM. In this particular case, we have an integer, a 32-bit integer n, and a 32-bit floating point t. And they're both 4 bytes of memory. All right, so you know what move R0 does. Okay. what does that do? I'm going to read the comment. We get a pointer to n, we get a pointer to t. All right, now we're going to teach you some opcodes. This is a floating point load, and so it's going to take this constant and store it into S1. What's S1? A register. Yeah, we got a whole bunch more registers. We got our R registers, you know about them? We got a whole bunch of S registers, which is why we don't want to use floating point, because what happens on an interrupt? We got all those 18 registers got to get dumped on the stack. So it turns out we're not going to use floating point because it slows down on interrupts. But there's a whole bunch of floating point registers. The S's are the floating point registers. That puts a 10 in there. The store instruction is going to, just like it always did, it's going to store the 0 into the n. So this makes n equals 0. Then we got some floating point move instructions. This one is going to move the value n into the floating point register S0 and then convert it right here. I'm converting the integer n to the floating point s. Right, so this converts s, now contains the floating point version of the integer value n. So n and s are so R0 and S0 are the same value, but one's in floating point form, one's in integer form. You can sort of imagine what multiply and add do, right? Multiplies and adds. Of course, I have to multiply and add S registers. Okay. And then the floating point store takes an integer pointer and stores it in. And that basically is the assembly code to implement a floating point operation. Because we see the n had to be converted from integer type into floating point type. I did a multiply and add and a store. In C, what does float do? Creates a floating point variable, remember? What does volatile do? No, volatile means remove all compiler optimizations. In this particular program, if I didn't use the variable t anywhere, if I store into t, and I don't ever read it, it's going to optimize it and take it out. So if it looked at this program and it would say, you didn't need to do any of that, right? In other words, even if I were to use t, it would say, why do I have to do it 4,096 times? I really only need the last one. And it will just do the last one. So volatile will undo the optimization. All right. So in summary, what we have is a way to store non-integer values. And if you do the following, if you remember this simple equation here, yeah, you'll be able to pass. You'll be able to do this problem on the exam. Remember this simple equation about what a value relative are, and we use the human input-output with decimal in the calculations. All right. Questions on fixed point? Yeah.
What's the opposite of volatile?
Okay. The question, what's the opposite of volatile? If you don't put volatile in, then it can optimize. For example, if I take port F, n equals port F, whatever, underlined, GPIO, underline port F, underline data, underline R, and I put it in a loop, right? So if I do this sort of thing, without calling this volatile, what the compiler do will optimize this into this statement. It'll only do it once and assume the value in n is the same and take it out, which is clearly not what you intended. So the opposite of volatile means optimize. Assume the value in the register equals the value in the variable. Okay? But in this case, it's an input port, and that wouldn't be true. Right? The value n is not identically equal to the GPIO. This guy can spontaneously catch fire. That's what it means. If your variable can catch fire. We'll see this also in on interrupt service routines, right? We're going to make it volatile so that because there's anything that's shared between the main program and an interrupt, anything between an interrupt and another interrupt, we'll make it volatile. All the I/O ports will be volatile. Good question. Any other questions? Yeah.
Is there any initialization needed before we use the S registers?
No. You said, do I need to? Well, you're going to need to turn the floating point on, and you'll notice in all my examples, I've shut the floating point off, by the way. So you'll have to explicitly turn on the floating point with some opcodes, because I'm going to shut it all off so when an interrupt happens, it doesn't have to push 18 registers on the stack. But it's pretty well set up, I think. That's a good question. Just like the other registers, right? Do I have to initialize R0? No. It's the only one the only two you have to initialize are what? The only program counter and a stack pointer have to be initialized. All right. All right. Well, next we're going to talk about. Okay. Next we're going to talk about the graphics. So let's go over.